Now that you've learned about how to use the chain rule, I'll explain why the chain rule works. First, let's talk about function composition. Here are the graphs of two functions, g of x and f of x. And we'll pick a value of x and call it a. Let's consider what it means to evaluate f of g of a. We'll begin by evaluating the function g at the input value x equals a, which yields the output value g of a. The value of g of a is then used as the input into the function f, which yields the output value f of g of a. So if we think about the graph of the composite function f of g of a, if we used a as the input, then the function f would produce the corresponding output value and would put these together to plot the coordinate on the graph. As we've illustrated, composing functions involves taking the output of one function as the input to another. This concept will be important as we examine the chain rule. Now, let's quickly recap the meaning of a derivative. We often write the derivative of a function f of x at the point x equals a as f prime of a. We can think of this graphically in terms of slopes. From our value of a, we have an amount of change of x and a corresponding amount of change of f. And the ratio of delta f to delta x is the slope of this green secant line. Since the graph isn't a straight line, this slope is only an approximation of the value of the derivative. But we can get a better approximation if we use smaller values of delta x. As delta x got smaller, the graph of the function f looked more and more like a straight line. When delta x is this small, we refer to delta f as df and delta x as dx. The value of the derivative of f evaluated at a is the slope of the tangent line. It's the ratio of df to the corresponding dx. So, over really small changes in x, the amount of change in f is f prime of a times as large as the amount of change of x. Now, let's put together the idea of composing functions with the definition of the derivative to understand why the chain rule works. On the left, we have the graph of the function g, and on the right we have the graph of the function f. We have already zoomed in a lot on these functions. Our goal is to understand the derivative of the composite function y equals f of g of x. We know that the derivative of a function at a value x equals a is equal to the ratio of a small change in f to the corresponding small change in x. So we want to know how much the output of the composite function changes as the input changes by the really small amount dx. Let's mark off x equals a on the graph of g of x, and we'll show how x changes by a small amount dx. Since we've zoomed in far enough for the graph of g of x to look linear, with slope equal to g prime of a, the corresponding change in g of x is equal to g prime of a times dx. Next, let's think about the composite function f of g. We need to think about the output of g of x as the input to f. So now, we'll think about the value of g of a as the input to the function f. And then, the change in g becomes a change in the input to the function f. The resulting change in the output of the function f is df. Since we have zoomed in, the slope of f appears essentially constant, so any small change in y is going to be f prime of g of a times as large as the corresponding change in x, dg. And now, since dg is equal to g prime of a times dx, we can write df as f prime of g of a times g prime of a times dx. Since the dx in both the numerator and denominator of this expression can be cancelled out, we've shown that the derivative of the composite function can be written as the product of the derivative of f evaluated at g of a and the derivative of g evaluated at a. This gives us the general chain rule for differentiation. The derivative of a composite function, f of g of x is equal to the derivative of f with the argument g of x multiplied by the derivative of g.